Alright, what's up? Here we go. Okay, in this video, I'm going to be covering everything to do with electricity and DC circuits. It's quite a bit of information, and I have quite a lot of questions to go through. This might take a little longer than an hour, probably. So, sit back, relax, and let your mind expand as you learn more and more about electricity and DC circuits. Okay, so here's the worksheet. I'll go through the theory in a second. I've got all the theory here you need. It's cut down and organized. It's pretty good. That's all you need to answer the questions. So that's there. And then you've got the questions themselves, which is a lot. That's a lot of questions. We'll go through a lot of questions. We'll go through 5 questions. They're all there. And all my answers are there for you as well. So a lot of written answers. So I don't want to hear any excuses about not understanding how to answer this question. You've got all my answers there. All right, let's jump into the theory. All right, so let's run through some theory. The key fundamental concepts that you need to grasp is voltage, current, and resistance. What are these things and how do they relate to each other? Because with every circuit, there's going to be a voltage supplied to it, which is basically the energy per unit charge being supplied to the circuit, and a current in it. How fast are these charges moving through the current, and a resistance, which is opposing the flow of charge. It's impeding our flow of charge. And so let's try and just first of all understand what those things are. So if we have a general circuit with some cell or battery, and the circuit has some resistance, supplying a voltage, it has a current in it and a resistance to it. Well, V equals IR. These are how these things relate to each other. And I think what confuses people is that if we increase the voltage, then what happens? Well, if we increase the voltage, for example, we also increase the current. I mean, you might be like, why don't we increase the resistance? Well, because the resistance is dependent on this material, on the dimensions of this material, and its resistivity, which I'll go into a minute. But if this is at a constant temperature, which it will be for omeric materials, is that the resistance stays constant. So this ratio of V over I is constant. So if we increase the voltage, will we increase the current? If we decrease the voltage, will we decrease the current? Right? And voltage is how much energy we have, or potential difference, per unit charge. So this is change in W, the energy transferred per unit charge. This is how much energy each unit of charge has. It's almost like you could think of it as it's what's moving the charge through the circuit. So obviously if we give the charge more energy, well then the current, which is the rate of flow of charge, then this is going to increase also. We're giving it more energy, so it's flowing faster. Right? And then let's say if we change this out for a different resistor of higher resistance, well, this is going to alter these things, because let's say we have a constant voltage supply. Well, if we increase the resistance, well, with a constant voltage supply, we increase the resistance, well, that's going to decrease the current, right? And it just makes sense intuitively. If we increase the resistance, well, it's impeding the flow of charge more. And so overall in the circuit, we have a lower current, right? Because when this has a higher resistance here, it's harder for this stuff to get through it. Well, then the flow around the entire circuit is all going to be the same, and it's all going to be decreased. It's not like the flow of charge in here, or I in here, is less than I out here. No, the entire circuit will have a lower current. Right, so you need to be clear about what voltage, current, and resistance is saying. What are they saying? And another way to think about current is to do with the dimensions of the wire itself, right? The current is moving through this wire, and it's related to the, you know, the average mean drift velocity of these electrons, because the charge is electrons basically flowing through the circuit. And so, you know, it's related to that. Also the charge, which is always going to be E in this case, because we're always going to be dealing with electrons. N is the number density, so how many electrons we have per unit, I mean per unit volume. And area, the area of the current, the area, the cross-section area of the wire. You know, varying these things are going to vary the current, the rate of flow of charge, because that's an important equation you should know. But these other two you should just be able to get from just thinking about what they are. And like I said, resists the flow of charge. You also need to know about electric power, and this can be derived from energy transferred over time. We substitute in here, you know, what's going on. We can basically rearrange and get P equals IV. And this is the power, the power of the amount of energy being transferred per unit time. And just like with potential difference, which is the same thing, saying like potential difference across this thing here, across this resistor, well, how much voltage is here and how much voltage is here? How much energy per unit charge do we have here and how much energy per unit charge do we have here? The difference between those two things would be the potential difference, right? Because obviously when these electrons move through this, they're going to have to use up some energy to get through this resistance, right? This resistor, they're using up energy, thus losing voltage. And so their potential difference between these 2 points are going to be different, right? And same goes with power. So there'll be some power dissipated within this resistor because it's related to the voltage. And if you substitute in V equals IR, you can get different equations for power. But P equals IV. Again, you should be able to derive that just from knowing the power is energy transfer per unit time. Now let's talk about resistance and resistivity. Well, resistance, like I said before, is impeding the motion of impeding the flow of charge. And so the resistivity is something to do with the material itself. And a way to remember this is we can just think about it. With all these things, you shouldn't be having to remember too much. So resistance equals resistivity all divided by A. The resistivity is to do with the material itself. You know, a higher or lower resistivity means, you know, a higher or lower resistance. And the length, you know, if we increase the length of our material, well, it's longer. So it's got more, like, it takes a lot more, has more resistance, right? It's longer, it's harder to get through. And you know, if we decrease the area, well, this will also increase the resistance, right? If we decrease this cross-sectional area, well, you could think of it like the particles in the resistor itself. Well, they're all going to be kind of closer. It's all going to be closer together, and it's just got a smaller, tighter thing to push through, and so it's going to be harder to get through. You know, if we increase this area of this wire, well, it's going to be easier to get through. Maybe that's one way to think about it, but this is an important equation. And so increasing that resistance, well, we need to actually change either the resistivity, so the actual material itself, we need to lengthen it, or change its cross-sectional area. Now, resistance is also dependent on temperature. So conductors that do not obey Ohm's law are described as non-ohmic. And so this means that, like I said before, we have a potential difference. There's energy being used up when we're going through a resistor by these by this unit charge, or this flow of charge. And the energy can be dissipated and transformed into temperature. And, you know, with some materials, when we increase the temperature, well, that's going to also increase the resistance. For example, like for these kind of materials, when we increase the temperature, that increases the resistance. And there's ways to think about this. I mean, if we increase the temperature, maybe there's more vibrations in the particles of the material, of the metal, so it's harder to get through. You know, there's more collisions going on, something like that. there's different models of ways to think about this, but you just need to understand there's a relationship between temperature and resistance. And then there's different like types of things that we could put in the circuit: thermistors, diodes, light dependent resistors. These are all things in which you should read through this, and we'll go through questions on it, but you should read through this. That they do different things to resistance, voltage, current. There's different relationships going on here, right? But it all comes down to voltage, current, and resistance. And we can put different things in the circuit which react differently to these different variables of voltage, current, and resistance. For example, like a thermistor, like a negative temperature coefficient thermistor, well, as temperature increases, the resistance decreases, which is different from this one. And so that's that case. So you just have to know that. And like diodes and stuff like this, there's questions, all these questions on the worksheet. Okay, and now so Kirchhoff's laws. What's going on here? So Kirchhoff's laws, there's two laws here. It basically says that the current in equals the current out. So the current in to any point in the circuit equals the current out. It's just basically the conservation of charge. That's an important law. And the other law you need to know is the second law, which is EMF and voltage. The sum of the EMFs around a closed loop or a circuit is equal to the sum of the potential differences around that circuit. And you can use these two equations to derive these things, where you get resistance, the sum of resistors in a series and the sum of resistors in parallel. You can use them to derive these equations, which is 1 over RT. The total resistance for these two things would be 1 over R1 plus 1 over R2. And this is to do with like if we have, might be a really bad explanation, but fuck it. Okay. R1 and R2. And we have a current flowing here. And then we'll have, as I said before with the law 1, well, we have some current flowing down here and some current flowing down here. But the currents, this current here will equal to I1 plus I2. Conservation here of the current. And because of that, we'll have a certain amount of current going down this sort of, what do you call it? I don't know, branch and this branch, and they'll be different and they'll be dependent on the resistance, the amount of current, because the way to derive this is through, well, you have to know that the voltage down either one, the potential difference across this resistor and the potential difference across this resistor are the same. There's no change in the voltage across either of these two branches. The voltage here will be the same as the voltage here. That's important to know that. That will help you with a lot of questions. The voltage going down this branch and the voltage going down this branch are exactly the same. Why is that? Well, it's because the current is, let's say this resistance is bigger. Well, then the current on this one will be smaller than the current on this one. They're relating to each other to keep this thing constant. Right? And also the EMF. Oh, there's so much theory to go through. I feel like I should just jump into questions. Maybe I'll just go on here. Also, the EMF is the sum of all of the potential differences. So if you have something like this, an EMF, and the difference between EMF and voltage or potential difference, the EMF is what's being transferred to the charges per unit charge, the amount of energy being transferred per unit charge, whereas the potential difference is how much of that energy is being utilized. And so there might be a potential difference of V1 across here and a potential difference of V2 across here. Well, the EMF, E, is going to equal to V1 plus V2. This is basically just saying that all the energy generated in the battery and transferred to these charges is being used up throughout the circuit. Basically what it's saying. And so these two laws are important. So far, you need to just understand whatever. So these two laws, and from these two laws, we can derive these series and parallel resistance. And finally, practical circuits. So in actuality, these cells or batteries are going to have an internal resistance, and the internal resistance is going to, you know, affect the outward voltage supplied to the circuit itself. And we can relate those two and derive this equation through the sum of EMF. The EMF equals the sum of the voltages, or the potential difference in the circuit. So it'd be the sum of this EMF here supplying will equal to, well, the potential difference across this internal resistance plus this potential difference across this, you know, external resistor. And then, you know, from that, we then have different things, different ways that we can set up the circuit to produce different things. We have things like potential dividers, which the potential is divided. We divide the potential supplied to the circuit. We do this through varying the resistance on some resistor. And there's a way to do that, so read through that. I don't have enough time to go into detail all of these. Potentiometer. This is basically, well, we have a length of string and we vary it, and this, you know, this varies like we vary the length, this varies the EMFs, you know, supplied. It compares EMFs basically. We'll do a question on this and a question on this, so do not fear. And then you've got all these like different component names which do different things. And you got the questions. Maybe my explanations weren't too good, but let's just jump into the questions and we'll consolidate them. Right, question 1. A metal wire is used to connect the power supply to a lamp. The wire has a total resistance of this and a resistivity of this, and the total length of the wire is this. Well, we want to show this, the cross-sectional area of the wire. This is just going to be from this equation. All these equations are on the worksheet. So therefore, we need to rearrange for A. It's going to be rho L over R. Resistivity is 2.6 times 10 to the negative 8. The length is 59. And the resistance is 3.4. This is going to take a while, you know, to go through all these questions, so you know, I might crack a few jokes, because it's a lot. I'm feeling some resistance towards doing these questions. 4.5 times 10 to the negative 7 meters squared, which is what they wanted. Cool. The potential difference across the total length of the wire is this. Calculate the current. Well, we have a potential difference across it. And we know the resistance of it. Well, V equals IR. Therefore, I equals 2V divided by I. V divided C. Yeah. Ooh. Yeah, boy. Just gotta shake it off, you know. Been not feeling it recently. 3.4. Right? 1.8 volts divided by 3.4. 1.8 divided by 3.4 is 0.2, well, 0.53. 0.53 amps. The number density of free electrons is this. Calculate the, well, this is from this here. I equals ANVQ. And because it's electrons, well, I equals ANVQ. But this Q, like I say on the worksheet, is E, because the charge is electrons. So 1.6 times 10 to the negative 19 coulombs. They give you that on your formula sheet. That's the charge of the electron. And so if we want the average drift speed, well, just rearrange for V. V equals to this. V equals to I over ANE. It's going to equal to I, which is this is 0.53 divided by A, the cross-sectional area, which was this, 4.5 times 10 to the negative 7. Yep, times N, which is this number density, 6.1 times 10 to the 28, and then times this 1.6, 10 to the negative 19. Boom, squeeze it in. Okay, 4.5 E negative 7 times 6.1, 8 times 1.6 E 19, 0.53 divided by that. 1.2 times 10 to the negative 4. 1.2 times 10 to the negative 4. I don't wanna know. Okay. A different part of the wire carries current. The wire has a thin part. Okay, so the wire has this thin part, so obviously there's going to be a decrease in the cross-sectional area. State and explain how the drift speed of the free electrons in the thinner part compares to the rest of the wire. Okay, whenever they ask to do this, we need to look at the equations. Okay, so drift speed is equal to this, I over ANE. Right? Well, throughout the entire thing, there's going to be a constant current. And the number density will also be constant, and E will also be constant. None of these things are changing, so this entire value here is constant. Therefore, if we decrease this, so we decrease the cross-sectional area, well, that means, because they're inversely proportional to each other, if we decrease this area, well, then we're going to increase the average drift speed. Therefore, we increase average drift speed. State and explain whether the power dissipated in the thinner part of the wire is the same, less, or more than the power dissipated in the equal length of the rest of the wire. Well, power equals IV. And in fact, we'll make it, we substitute an IR here, V equals IR, this is I squared R. Why do I do that? Because I know resistance is altering here. So resistance equals rho L over A. In equal length. So this length is constant for this thin part as the thick part. It's the same material, so that whole thing is constant. And so we're decreasing this, the cross-sectional area, which means we're increasing the resistance. So decreasing cross-sectional area, this increases resistance in the wire. So we've got an increase in resistance in here, and if we have an increase in resistance, well, because P equals I squared R, if we increase the resistance, then we're also going to increase the power, because the current in both of these things, the thick and thin part, is the same. So therefore, as current is constant, that means power dissipated in wire is increased. What did they say? More. It's more. More than the thicker part. Oh, that's it. That's all she wrote, folks. 3 resistors, that, and that. Sketch a diagram to show how 2 of these 3 resistors may be connected to give a combined resistance of 60 ohms. Well, we know this. I can see that it won't be in series, right? Because I can't add any of these together, because in series the R total is R1 plus R2. There's no way I can combine these 2 together to get 60, so it's going to be something to do in parallel. And so how can I add 2 resistors together to get 60? We just need to think about it. R total, well, 1 over 30, you can just literally just combine some. 1 over, I'm going to guess it's 1 over 90 plus 1 over 180. It is 1 over 90 plus 1 over 180. This gives us 1 over 60, so therefore RT will be 60 ohms. So if we put these 2, a 90 ohm and a 180 ohm, in parallel like this, or the total resistance together, if we were to combine it into one resistor, will be 60. This. A potential divider circuit is produced by connecting 3 resistors in... Okay. The potential divider provides a output voltage of 8. Label. Okay. So how do we set this up to give an output voltage of 8 volts? In potential dividers, the potential is being divided in ratio to the resistance. There is an equation which is derived for you, but you can just think about it. Where's it at? It's this. But let's say if I was to put these 2 here, 90, 180, and then 30 here. Well, this total resistance here is 60, and this total resistance here is 30. And so the total resistance across the whole thing is 90. All right, 30 plus 60. And as a ratio, 60 divided by 90 times 12, well, this is going to give us 8. That means this output voltage, this output, is going to equal to 8 volts here. So if we set it up like this, the ratio of these resistors, for the ratio of this total resistance to this ratio of this total parallel resistors to the total resistance is 60 over 90, and that's how it's dividing up this total EMF supplied to give 8 volts out. If I change this, well, then this will change, but it wants to know how to set it up to give me 8 volts. Read about more on that on the worksheet. Define the ohm. Voltage equals I R. R, which is the unit, ohm is the unit for resistance, is equal to voltage over I. So voltage is in volts and this is in amps. So it should be volt divided by here. A wire made of resistivity this, length L of the wire is gradually increased. Assume that the volume of the wire remains constant as its length increase. Show that the resistance, so we want to show this. Okay, so before we start, well, let's look at our equation. And so we're increasing the length of the wire. Length of the wire is increased. Assume that the volume of the wire remains constant. Okay, the volume is going to equal to the cross-sectional area times the length, right? This times this gives us the volume. And so therefore, if we want we don't know what's happening to A, so if we rearrange this, we can say A equals to V over L. And this is going to equal to L over V over L. V over 4, V over L. Which gives us L squared over V. Why did I substitute this in? Because I don't know what's happening to the area. It doesn't say it remains constant, but it says that the volume remains constant. So I find out what the volume is and substitute it in, because then this thing here remains constant. And if this thing here remains constant, well, we can say that R equals to, you know, rho over V times L squared. That's what that is. This is constant. If this is constant, well then R is proportional to L squared. A battery of this with internal resistance R. Okay, this is a variable resistor, means it varies the resistance. Okay, so this comes down to sum. So just quickly before we start, the sum of the EMFs equals the sum of the potential differences. So in this case, it'd be E, what's supplied here. So capital E. E, what's supplied here. Well, this is going to be the potential difference across R, which is VR, plus the potential difference across the variable resistor. This is going to equal to, well, this is going to equal IR, right? Current V equals IR, plus we'll just keep this as V. This is V here. So therefore V equals to, if we rearrange this, will be E minus IR, which is minus I minus R. Just rearranging this thing into this form. This is Y equals MX plus C if we plot I and V against I, like they do here. This is important. So the gradient is the negative of the internal resistance. Okay, so use this figure to state the EMF E. Well, using this, which I just said, this is plus C. So where it intersects the y-axis, and the y-axis is V. So the EMF will be whatever this point is. And this point is, what, 2.1234. This point here is E, which is 2.4 volts. This is an important equation, but it can be derived from Kirchhoff's second law. Use the figure to determine the power dissipated in the resistor when there is a 5 amp current. When there's 5 amps of current, potential difference across the variable resistor is what? This is 1.123, 1.3 volts here. So power equals IV. At 5 amps, we have 1.3 volts. It's just 5 times 1.3. I'm not quite sure why this is 3 marks, but there you go. 6.5 watts. State what is represented by the value of the gradient of the graph. Well, as I just said before, by rearranging this thing, remember I'm just finding this from Kirchhoff's second law. The EMF equals, in a closed loop, equals the sum of the potential difference across here and plus the potential difference across here. Basically just saying all of the electromotive force is being used up by the circuit. All the gradient is just minus R. Let's keep going. Define electric potential. You'll see as I do more questions, you're understanding more. I know you are. Define electric potential difference. This is the energy transferred per unit charge. The battery is connected to two resistors, X and Y. The resistance of X is greater than the resistance of Y. Resistance of X is greater than the resistance of Y. State and explain which resistor dissipates more power. Well, power equals IV. which will equal to IR I squared R. Okay, the current, why do I do that? Because I want R involved. They're relating R, so I want R involved when I'm talking about power. Okay, so the current in both X and Y is the same. This is resisting the current. This is resisting the current. So the overall current of the circuit is the same. Current here is the same as current here, same as current here, same as current here, same as current here, same as current here. Same as the current in your room. No, not that. But the current is the same everywhere. Okay, and if the current is the same everywhere, that means this is constant. So if Rx is greater than Ry, well then the power dissipated in X will be greater than the power anticipated in Y. Px is greater than Py. If the resistance of X is greater than the resistance of Y, well then the power of X will be greater than the power of Y because they have the same current. A battery of this internal resistance, this. Okay, so we have a total charge that moves through resistor P at a time interval of this. During this time, resistor P dissipates this much energy. The current in the resistor Q is this. Okay, assume the EMF. Okay. Calculate the current in resistor P. Well, current is the rate flow of charge. So we have 650 coulombs of charge flowing in 540 seconds. That's the current, baby. 1.2 amps. 0.2 amps. Okay. Right, so that means there's 1.2 amps flowing down here. And 4.5 flowing down here. But the sum of these two things will be the current flowing down here. Conservation of current. Potential difference across resistor P. Oh. P equals IR. P equals IR? No. V. Why not V equals IR? Well, I don't know what the resistance of V is. So V is, we have the energy dissipated. So this is V equals change in W over change in Q. How much energy per unit charge? We have 4,800 joules of energy. And we have 650 coulombs of charge. Oh, 7.38. 0.38 rounded will be 7.4 volts. Potential difference across P is 7.4 volts. The internal resistance of R, well, this comes down to this equals the EMF supplied equals the total potential differences. So this would be, well, the potential difference will equal to V plus, remember that, okay, so you might think it's, well, VP plus VQ, but the potential difference across these two things are the same. All of the energy is being used up. Plus IR. So we want R, or V, this V here is going to equal to this. The potential difference across this. Just the potential difference across this. It's the same thing. But the sum of the EMFs, the sum of the EMFs equals the sum of the voltages, the potential difference in a closed loop, in this closed loop, or this closed loop. If you were to combine them and then do it, it would be the same thing, but in this closed loop. So in this closed loop, it doesn't mean the 9 equals 7 because remember there's 7.4 down here and 7.4 down here. The voltages are the same down both branches. But in this closed loop, it's going to equal to, the E will equal to the voltage across this, the voltage across P, plus the potential difference across here, the voltage across the internal resistance, VR. And this is IR, VP we have. So R equals to E minus VP over I, which will equal to 9 minus 7.4 divided by I, which is the current in this circuit. The current in this circuit is going to, or the current going through this battery, in fact, is going to be whatever this is, this I here. Right? And this I is just 1.2 plus 4.5. If we want, this I is the current flowing through this resistor, this internal resistance, and the current flowing through this internal resistance, you know, is when they meet up. So this thing flowing through here, well, this, you know, I flowing through here is just going to be, you know, I in P plus I in Q, which is 1.2 plus 4.5. Also known as 5.7. So this is V divided by 5.7. 9 minus 7.4 divided by 5.7 is what? 0.28 ohms. State Ohm's law. This is, you know, V equals IR. This is saying that the current through a conductor is directly proportional to the potential difference across it. Across the conductor. Across the conductor. You know, as long as temperature of our conductor is constant. The temperature increases, well, like we saw, the resistance is going to do something. It's going to increase. So we've got a variation of the current and the potential difference of a filament lamp. The resistance of the filament lamp increases with the potential difference. Okay, state why this is. Well, because, you know, resistance equals V over I, right? When we increase, so that's whatever, if we pick a point, whatever, like, if we pick a point, so this ratio of V over I, this is increasing, right? And if this is increasing, well, that, like, it's increasing, right? Because, you know, we pick a point here, this is like 2, so 2 divided by, I don't know, like 0.75. 2 divided by 0.75. And then up here, well, it's 12 divided by 2. So clearly, clearly this is bigger. So the resistance as we're going up here is getting bigger due to the increase in temperature. So this ratio is increasing, so thus the resistance is increasing. Ratio is increasing as we move along this graph, this ratio. Explain why this happens. Well, the resistance varies this way because, yes, the current is increasing, and when current increases, the temperature increases. When the current increases, the temperature increases. When the temperature increases, the resistance increases. Therefore, the resistance increases. This figure. Okay, so we've got this, and it's connected to a potentiometer. Okay, the battery has no internal resistance. When the slide of the potentiometer is at its midpoint, on when the current in the battery is this. Okay, determine the current in the lamp. Well, potentiometer, this is dividing up the potential. Yeah, potential dividers. This is dividing up the potential as we move between here and here. So if it's halfway between that, that means 6 volts is going here and 6 volts is going here. This is dividing by half. So, the voltage in P is 6. So therefore the current, V equals IR, therefore I equals V over R. This is equal to 6 over the resistance. What is the resistance? Well, current in the lamp, P. Current in the lamp, P. Determine the current in the lamp, P. Yes, we don't need to do that. We can just look in the graph. Okay, at 6 volts, what is the current in the lamp, P? This is showing the variation of the potential difference, the current in the filament lamp. So when we have 6 volts going through it, 1.6. So this would be, at 6 volts, we have a current of 1.6 amps. Not 1.6, 1.556. It's 10, so they're 0.05 each, so 1.55, my bad. 1.55. The total power dissipated in the lamps, P and Q. P equals IV. So the total current will be the power dissipated in P plus the power dissipated in Q. What is the power dissipated in P? Well, the power dissipated in P is I, which is 1.55, times the voltage, which is 6, plus the power dissipated in Q. What is the current flowing through Q? If the current flowing through P is 1.55, well then the current flowing through Q is 1.55. 1.55 times, and 6 volts as well. This is dividing up the voltage, 6 volts here, 6 volts here. .6 watts. 18.6 watts. So 19 watts. The resistance of the potentiometer between its points A and B. Okay, well we know the current flowing down here is 1.55 amps. And the current supplied by the battery, the current in the battery, is 1.78 amps, well, you know, the current here is being split. So the current down this thing here in this potentiometer will be 1.78 minus 1.55. Conservation of current. Kirchhoff's first law. Kirchhoff's laws, man. You need them. So the current flowing through the potentiometer is 0.23 amps. Okay. Right? This 1.78 is being split to here and here. 1.55 down here, so then 0.23 down here. Okay? And so therefore the resistance is V over I. And so yeah, we can just use the graph. Wait, can we? V. The resistance of the potentiometer between A. We've got this current. What's our voltage? It's just going to be 12 volts, no? 12 divided by 12 divided by 0.23. Yeah. 2 ohms. Right, so we have 12 volts going down here, like I said before, because this is an important concept. There's 12 volts going down here and 12 volts going down here. Voltage stays the same. It doesn't split like current. This is going to be 12 divided by 0.23, which gives 52 ohms. 52! The slider moved to end A, stay and explain the effect on the brightness. Well, let's just read through this. But basically, look, when we move the slider to this end here, this will be going to 0. R2 will be going to 0. If it's going to 0, well then there's no voltage output. So at end A, there's going to be no voltage, or the potential difference. Potential difference across amp B will be 0. So the brightness will be 0. Lamp Q, well, when we slide this thing here, well then basically all of the potential, well, it's all going to go to lamp Q. So, you know, the PD across lamp Q will increase. If we have an increase in that, well, then the brightness will increase. All right, last one. Okay, so state Kirchhoff's law. Kirchhoff's law, second law, is the sum of the EMFs equals the sum of the potential differences around closed circuit. This is this. Battery of this electromotive force, internal resistance this. It's connected to a wire. Okay, the wire XY has a resistance of this and a potential difference of this across it. Okay, calculate the current in the wire. Well, V equals IR, therefore I equals V over R. There's a potential difference of this and a current across in a resistance of this. Will be 1.8 divided by 0.92. So we have 2 amps running through this bad boy. Okay, the number of free electrons that pass a point in the battery of this. Okay, we know that current is changing Q over changing T. We have if we have the current going through this, well, that's going to be the current throughout the circuit. Current is conserved. And so charge is conserved. So current, so therefore the charge will be I changing T, changing Q, whatever. And so this will give us the total charge that's passing through the battery in 45 seconds. It's 2 times 45. It's 90. 90 coulombs of charge. So if we want the number of free electrons that pass in 90 coulombs of charge, well, the charge on a single electron is 1.6 times 10 to the negative 19 coulombs. So if we want the number, well, it'll be we have 90 of them, where we have 90 coulombs of charge, and therefore divided by 1.6 times 10 to the negative 19. It's 5.6 times 10. 0.6 times 10 to the 20. That's how many electrons. If in 45 seconds we are producing 90 coulombs of charge, that's how much we're producing. And so if each individual electron has this much charge, and we want to know how many there are, well, we do 90 divided by that. And they'll show us how many of these are in 90. What's that? The resistance R. Okay, if we want to find the resistance R, well, we know the sum, the EMFs, the sum of the potential differences. Okay, so that means E equals to the potential difference across the wire, plus the potential difference across the resistor, plus the potential difference across the internal resistance. The potential difference across the wire is 1.8. EMF is 4. This is 1.8. This is IR. We have 2 amps running through it. So this would be 2 times 2 times R. IR, 2 R plus the V, the potential difference across this will just be 2 amps times 0.35. 2 times 0.35. God, it's so messy. Okay. Therefore, we get 2 times 0.35 plus 1.8. 4 minus that. We get 2R equals to 1.5. So R will be 2. 4 divided by 1.5. No. 1.5 divided by 2. What am I on about? A cell. Okay, so this is the. So this is this. This is a common thing that comes up. So we have a cell of EMF. Cell of EMF 1.2 volts is connected to. Okay, so this is a common diagram. Connected to P, the galvanometer reads 0 at distance XP. So this reading 0 means basically when this thing reads 0, it means that the potential difference across here, VXP, equals to the potential difference across here. I guess, what do we call it? No, when this thing reads 0, that means that this potential difference equals this, or equals the EMF of this. So the potential difference across here equals that. That's what it means when this thing reads 0. So to calculate the length, well, we have the rate. So minus the ratio E, so VXP divided by VX XY. So the potential difference across between here and here and here and here, this is going to equal to the, the current running through the wire times the resistance across this part of the wire divided by I times the resistance across this part of the wire, but across the entire wire. These things will just cancel. And then if we want the lengths, well, we know that R equals rho LA over A, right? And so this is staying the same, this is staying the same, it's the same wire, so R just equals this. So I guess you could, you could plug it all in if you want. So L over XP divided by A divided by rho L over XY divided by A. These all cancel, so you get that. Okay, so the ratio of the potential differences between XP and XY, and remember the potential difference between XP and XY are going to equal to this. So then we can figure it out. But basically the thing with this is when this is 0, this means that this is equal to this. And so therefore this is going to equal to 1.2. For more information on that, just read this. And VXY, well, that's just equal to 1.8. Potential difference across the entire wire divided by 1.8 is going to equal to, well, the length XP is given here 0.3, where this thing reads 0, is equal to 0.3 divided by LXY is the total length of the wire. Therefore, the total length of the wire will just equal to L, so 0.3 times 1.8 divided by 1.2. 0.45 meters. 0.45 meters. The fixed resistor is replaced by a fixed resistor of greater resistance. Say and explain the change of any that must be made to the position P on the wire. Okay, so if we increase this resistance, so we change this resistance, we increase it, what happens? That's what's asking. We know that VXP over VXY equals to LXP over LXY. Okay, so we want to know what happens to this, right? It's asking, this is the point where the galvanometer equals 0. This point P is where it equals 0. And so if we increase this resistance, well, that means that more of the voltage, the EMF supplied, will be across here. And so that means less of the voltage will be across this wire. So this thing here is going to decrease, right? If we increase the resistance on this, that means that the potential difference across this thing here will increase, right? It's harder to get across it. It takes more energy, more potential. And so therefore, because the sum of the EMF, all of the voltage supplied must be distributed between the wire and this resistor and this as well, but this will be the same. Well, that means that this thing will decrease. The potential difference across here will decrease. So that means this thing decreases. And if this thing decreases, well, let's say, and the length of the wire is the same, we times through by this. So we get, VXP times LXY. You just need to look at the equations. So this thing, we now concluded this thing decreases. I guess I'll say that. So the potential difference across wire decreases as whatever, we'll just say that. Decreases. Potential difference across the wire decreases. This thing is a constant, right? This is definitely a constant, and this is a constant as well, because this point is going to be 1.2. This point is where this thing equals 0, so it's going to be 1.2. So this is a constant, this is a constant. So if we have a constant and we divide it by something that's getting smaller, well, this is going to get larger. If this gets larger, well, then that means that this point is going to be closer to y. So I guess what we can say. So, you know, length. Oh, this is x p. Length xp will increase. I'm fatiguing. Increase. So, you know, point will get closer to y. All right, and that's just looking at the equation, seeing so increase and see what happens. All right, that's it. It was a lot. It was a lot. And now I'm going to talk about technology and machinery. What's going on with that stuff? I've been doing a lot of thinking recently. I've kind of changed my tune on how I feel about machines and technology. I did used to see them as quite detrimental, and in a sense they are to humanity. But I've changed my tune. I've done a lot of thinking, a lot of deep thinking on this. And let's get serious for a second. You know, what is really going on with these machines, with this technology? Physics, in a sense, here we're trying to give a story, a logical and rational story for how these machines came about, how this world that we see right here came about. And if you increase your attention and awareness and just look around, machines are deeply integrated into our culture and society. Even in a sense right now, you are communicating with a machine. You're looking, the machine is producing all of this audio and me speaking and all of this. Like, it's producing it for you. You've never met me. You have a relationship with a machine. Yeah. That's what, in a sense, in a real sense, that's what's happening. And unconsciously, for people that aren't paying attention, we really are becoming symbiotic with machines, meaning we're developing a relationship which is, I think, now beneficial for both machine and human. I mean, we're not actually building this stuff. I mean, there's not people sitting in a factory building it. No, a machine built this machine, and this machine gets better, and the things building it get better. It's like, what is going on here? There's like a proliferation of machine production and machinery in the world, this technology. And when I think about code and stuff like that, what is that? I'm telling a machine to do something. It's a way to communicate with the machines and get them to do things. People ask the question, you know, is a machine more intelligent than a human? I mean, I don't think that's the right question to ask. There's a difference in intelligence, clearly. A machine can do ridiculous computations to do with mathematics, let's say, for example, where a human being can't. But if you try and get a machine to do something simple like take out my trash, I mean, it's going to take millions and millions of dollars to build a machine to do that. So there's a difference in intelligence, and a child could bloody take out my trash. Yeah, I'm trying to reconnect with what I was feeling like when I was thinking about this, because I got into this, my mind got traction, and I really started to see, what are these machines? Like, what is going on here? Like, what is really going on with these machines? Like I said before, yes, physics is giving us some rational story for how these machines came about. But really, when we look into it, we don't, so some electrons, some particles, we learn equations that made these, which allowed us to manipulate them and move them around circuits, and these circuits then could build into computers and these technologies which now have the capacity they have now. That's not a rational jump. That's almost like magic. Like, what the fuck is that? Seriously, like what the hell is that? How is that even possible? I get the sense that utility, using machines to be more productive and make our lives easier, should have been like a side print, should be a side print in how to use these technologies. And it seems like we've got obsessed with using them for utility. Like, you know, like Uber and shit like this shit is organization, and I don't feel like that's the way we should be using them. It's like we found a chest filled with alien treasure and we're using it to reach the top shelf. I mean, obviously it seems like everything is corruptible for human beings. We can corrupt anything. And I feel like machines aren't any different. I mean, if you think that these machines and these platforms and the internet and social media and all this thing is not being corrupted and manipulated, you're out of your fucking mind. Of course it is. We're connected across the world. Of course people are going to corrupt it and try to get it to be used for things of manipulation, control. Of course they're going to use it that way. But if somehow we could see past that and move past that and stop trying to corrupt each other, I mean, these machines, God knows what these machines could be used for. They could change everything, really. I mean, they already have in a sense, but I don't know what I'm trying to get at. What I'm trying to get at is I don't understand what's going on with these machines. Really, how did these come about? I mean, seriously. And it feels like magic because you can tell them to do something. I can go on my phone and I can order a pizza. So with my phone, I'm giving it some language in the form of English, which is then being computed through computer programming language to then ping messages through this ethereal thing, just through the air, to then go to a restaurant where they start to create a pizza and then give it to someone, and then that someone brings it to me. So my little thing is created a cascade of events which have happened. So it's deeply integrated into the physical world and what's going on. I mean, it's remarkable and it's almost magical. And this is actually not what I was planning to talk about, but I think there's something extremely interesting going on with these machines, with these technologies. And it's not something rational and obvious. So yeah. I guess like the video. This is quite a lot of work for me to go through this. It was quite stressful as well. Found it quite difficult to go through it all and organize it all. It's just in the organization of all of it. And teaching it all and putting it all into one video is quite a lot for me, but hopefully it was useful. I know some of my explanations in the video weren't that great, but I've been feeling quite stressed recently, I think. I think I need a break of some sort or something. But yeah, make sure to like the video and I hope you do well in your exams. And I've got one more video to do on particle physics, which is a deep love of mine, so I'm looking forward to that. Peace out.